Picture yourself standing in the middle of an endless desert, the sun beating down on a landscape of sand and rock stretching to the horizon in every direction. Now imagine someone telling you that beneath your feet lies the bottom of an ancient ocean, that you are, in fact, walking across what was once a thriving seafloor, teeming with marine life, swaying corals, and swirling currents. It sounds like the premise of a science fiction novel, yet this is not fantasy. This is our planet's hidden reality, a geological truth preserved in stone, sediment, and fossil all around us. Today, we're setting out to explore one of Earth's most captivating mysteries, the story of 21 ancient shorelines concealed thousands of miles inland from any modern coast. These aren't just lines on a map or abstract ideas. They are tangible remnants of worlds that have vanished, of oceans that once stretched where today we find deserts, mountains, and forests. Each of these forgotten coastlines holds clues to monumental shifts in our planet's history, epochs when continents collided, ice ages rewrote sea levels, and environments transformed in ways that challenge everything we assume about the stability of the world beneath our feet. This journey will take us from the heart of the Sahara to the high plateaus of Tibet, from the depths of the Amazon rainforest to the salt flats of North America. We'll uncover how these shorelines were formed, why they disappeared, and what they can teach us about Earth's past and its future. You'll come away with a new perspective on the ground you walk on, realizing that landscapes are not permanent, but pages in an ongoing story of change and adaptation. So settle in, open your mind to the extraordinary, and join me as we travel back through millions of years to trace the echoes of oceans that once were. So how does a coastline end up stranded in the middle of a desert or perched on a mountaintop? The answer lies in two of the most powerful and relentless forces shaping our planet: the slow, monumental dance of tectonic plates and the dramatic, cyclical rise and fall of sea levels. Think of the Earth's crust not as a solid, unbroken shell, but as a giant jigsaw puzzle made of massive plates that are constantly, imperceptibly moving. Over millions of years, these plates collide, pulling ocean floors downward into trenches or crumpling continental edges upward into towering mountain ranges. A region that was once a low-lying coastal plain can be thrust high into the air, lifting its ancient beachfront with it and leaving it preserved thousands of feet above the modern sea. Conversely, other areas can sink or subside, creating vast basins that ocean waters then flood, extending the coastline deep into the interior of a continent. This tectonic drama sets the stage, but it's often partnered with another colossal player, climate. During ice ages, immense volumes of the planet's water are locked away in massive glaciers and ice sheets, causing global sea levels to plummet and exposing vast stretches of continental shelf that become dry land. When those ice ages end and the world warms, all that melted ice flows back into the ocean basins, causing sea levels to rise dramatically and inundate those same low-lying areas, sometimes for hundreds of miles. This constant push and pull between land and water, driven by geology and climate, continuously redraws the world's map. But how do geologists actually read this erased map? They act as detectives searching for clues left behind in the landscape. The most obvious evidence is often found in the rocks themselves. Finding a layer of limestone packed with fossilized seashells, coral, or the bones of marine reptiles in the middle of a dusty plain is a dead giveaway that the area was once underwater. Similarly, certain sedimentary structures, like the rippled patterns left by ancient currents on a seafloor, can be found frozen in stone far from any shore. The very shape of the land can also tell a story. Look for long, flat terraces carved into a hillside. These wave-cut platforms are the unmistakable signature of where powerful waves relentlessly pounded a cliff face for centuries, a cliff that is now high and dry. Sometimes the evidence is even more subtle, like the chemical signature of seawater trapped within mineral deposits or the specific types of rounded, water-worn pebbles that only form on a beach. By patiently piecing together all these different clues, scientists can not only confirm the existence of a long-lost ocean, but also begin to reconstruct its depth, its salinity, its currents, and even the creatures that called it home. This isn't just an academic exercise in understanding the past. It's crucial for preparing for the future. By studying how sea levels have changed in response to past climate shifts, we can create better models to predict how our own coastlines will transform in a warming world. Unraveling the forces that submerged entire regions or raised seafloors into peaks gives us profound insight into the incredible dynamism of our planet, a world that is never truly at rest. Now let's journey to one of the most striking examples of this planetary transformation, a place that perfectly illustrates the sheer scale of these changes. We travel to the Sahara Desert, a vast ocean of sand so immense and arid it's difficult to picture it as anything else. But if we could rewind the clock by 100 million years to the middle of the Cretaceous period, we would be utterly submerged. We wouldn't be standing on hot, shifting dunes, but rather swimming through a warm, shallow, and incredibly vibrant sea. This was the Trans-Saharan Seaway, a massive waterway that sliced through North Africa, connecting the ancient Tethys Ocean to the Atlantic and effectively turning much of the continent into a sprawling archipelago. This wasn't a fleeting puddle. It was a dominant feature of the planet for millions of years, a marine highway teeming with life, and the proof is not hidden away in some inaccessible vault. It's lying out in the open, scattered across the desert floor for anyone who knows what to look for. Paleontologists working in regions of Algeria and Morocco have made breathtaking discoveries that shatter our perception of this landscape. They haven't found mere grains of sand, but the fossilized bones of monstrous marine reptiles like long-necked plesiosaurs and powerful, predatory mosasaurs. They've uncovered the teeth of ancient sharks and the massive, dinner plate-sized shells of extinct giant clams, all preserved in exquisite detail in rock layers that now bake under the relentless sun. These aren't just isolated fragments. They are the assembled skeletons of a complete and thriving ecosystem, a world that was suddenly frozen in time and then left behind as the waters receded. Modern technology allows us to see the ghost of this sea even more clearly. Satellite imagery and advanced geological radar surveys have mapped the subterranean anatomy of the desert, revealing the outlines of long-buried river deltas, submerged channels, and vast sedimentary basins, all the telltale features of a coastline that hasn't seen water in eons. These tools let us trace the ancient shoreline itself, a boundary between a deep past and a dry present. But the real power of this discovery isn't just in the fascinating imagery of sharks swimming over future desert. It's in the profound lesson it teaches us about climate and environmental change. The Sahara's hidden ocean floor stands as a monumental testament to the fact that no ecosystem, no matter how permanent it seems, is truly fixed. A warm, shallow sea that supported such an abundance of life for so long was ultimately no match for the slow, grinding forces of plate tectonics and the planet's shifting climate cycles. As continental plates moved, the seaway was gradually cut off and drained. The global climate cooled, sea levels fell, and the region began its long, slow transformation into the hyper-arid desert we recognize today. This single shoreline, therefore, is more than a relic, it's a key. It unlocks a deeper understanding of how extremely fertile, water-rich environments can be radically altered and ultimately lost, turning from a cradle of life into a challenging, inhospitable landscape. In a world currently facing its own rapid environmental shifts, the silent, sandy testimony of the Sahara's oceanic past serves as a powerful and humbling reminder of Earth's immense capacity for change. Leaving the sun-scorched sands of the Sahara behind, we now travel to another continent defined by its stark, dry beauty, Australia. When we picture the Australian outback, we imagine a relentless landscape of red earth, scrub brush, and shimmering heat haze, a place where water is a precious and rare commodity. But this image of a perpetually sun-baked continent is, geologically speaking, a very recent development. To uncover its deeper history, we must venture into the heart of this vast land, to a region known as the Lake Eyre Basin. Today, it's a spectacular expanse of blinding white salt flats, a dry and cracked lakebed that only occasionally floods. Yet, this very same spot holds the key to a time when the entire interior of Australia was not just wet, but utterly drowned beneath a warm, shallow sea. During the Eocene epoch, approximately 50 million years ago, the world was a much hotter place. There were no ice caps at the poles, and sea levels were dramatically higher than they are today. At this time, ocean waters spilled over from what is now the Gulf of Carpentaria in the north and the Great Australian Bight in the south, converging to inundate the low-lying center of the continent. This wasn't a temporary flood, it was a long-lasting inland sea, a massive body of water that would have completely transformed the character of the land. The most breathtaking evidence for this vanished marine world was unearthed not by sophisticated machinery, but by the persistent work of paleontologists carefully sifting through the outback soil. Their most astonishing find, the fossilized bones of whales. Imagine the sheer improbability of discovering the remains of these giant ocean-dwelling mammals hundreds of miles from the nearest coastline, in the middle of the world's driest inhabited continent. It's a discovery that forces a complete mental rewrite of the landscape, but the clues don't stop there. The sedimentary rocks throughout the basin are packed with the fossilized remains of other marine life, sharks, sand dollars, and seashells, all silently testifying to a thriving ecosystem that once existed where there is now only dust and silence. This ancient shoreline is no longer defined by crashing waves, but by the subtle, haunting features of the modern outback, the vast, flat expanses of the salt lakes, the wave-like patterns of ancient sand dunes that once formed underwater ripples, and the layers of mineral deposits that precipitated out of the evaporating sea. The existence of this inland sea fundamentally challenges the stereotype of Australia as an ancient, unchanging desert. It reveals a continent with a dynamic and dramatic history, one that has been repeatedly shaped and reshaped by global climate patterns and the slow, powerful movements of the Earth's crust. The sea eventually retreated as the global climate cooled, and the landmass of Australia, riding on its tectonic plate, drifted further north into drier latitudes. The water evaporated, leaving behind the vast salt pans we see today as a ghostly, mineral residue of that watery past. This hidden sea is a powerful reminder that the environments we see around us are not permanent. The driest, most seemingly inhospitable places on Earth often hold within them the secrets of lush, water-rich worlds, proving that our planet's story is written in cycles of incredible transformation. From the sun-baked salt flats of Australia, we now plunge into the opposite extreme, the lush, teeming, and unimaginably vast Amazon rainforest. This is a place defined by its rivers, a sprawling network of freshwater that snakes through the deepest green jungle on Earth. It is the last place you would ever expect to find traces of an ocean, and that is what makes the next discovery so astonishing. Beneath that incredible weight of vegetation and the mighty flow of the Amazon River itself lies evidence of a time when this entire region was not a river basin, but a vast inland sea. During the Miocene epoch, some 10 to 20 million years ago, the world was warmer and sea levels were significantly higher. At this time, the Atlantic Ocean did not stop at the eastern coast of South America. Instead, it pushed inland, pouring through what was likely a much lower-lying landscape. This was not a gentle flooding. It was a major marine incursion that created a massive, shallow seaway stretching for hundreds of miles into the continent, effectively turning much of western Amazonia into a huge, sheltered bay. For millions of years, this warm, nutrient-rich water supported a completely different kind of ecosystem. The proof of this incredible transformation is buried within the very earth of the rainforest. Geologists drilling deep core samples and paleontologists examining riverbank cliffs have made finds that seem utterly out of place. Layers of sedimentary rock that are typical of calm, shallow ocean floors are interwoven with the soil. Even more definitive are the fossils, not the bones of jaguars or monkeys, but the unmistakable remains of marine life. They have found the teeth of giant sharks, the ossified skeletons of stingrays, and perhaps most convincingly, the fossils of microscopic organisms called foraminifera, tiny creatures that live exclusively in salt water. Finding these oceanic fossils deep in the continental interior is like finding a sandcastle in the middle of a forest. It simply doesn't belong, and its presence forces a complete reimagining of the entire area's history. This ancient sea did not just come and go without leaving a lasting mark. Researchers now believe this prolonged period of marine conditions played a fundamental role in crafting the Amazon's legendary biodiversity, which is one of the highest on the planet. When the ocean eventually retreated, driven by the continued uplift of the Andes Mountains which altered the drainage of the entire continent, it left behind a transformed world. The rich mineral deposits and the unique ecological niches created by the retreating sea provided a blank slate for evolution to run wild. Some scientists theorize that certain species we associate entirely with the Amazon today may have evolutionary origins that trace back to this marine past. For instance, there are species of freshwater dolphins and stingrays that are found thousands of miles up the Amazon River. Their closest relatives are marine species, suggesting their ancestors may have been left behind when the seawater drained away, adapting over eons to a new life in freshwater. This hidden shoreline does more than just rewrite the history of a single forest. It profoundly demonstrates the deep, fundamental interconnectedness of our planet's systems. It shows that the ocean is not a separate world, but an active participant in shaping the continents. The boundary between land and sea is not a permanent wall, but a temporary line, constantly being redrawn by the immense, slow-moving forces of geology and climate. The Amazon, a symbol of untouched terrestrial wilderness, carries within its very soil the indelible salt-stained signature of the ocean. Crossing now from the southern hemisphere's vanished waters, we arrive at a shoreline that once cut through the very heart of North America, a marine thoroughfare so immense it fundamentally reshaped an entire continent. For a staggering 35 million years during the late Cretaceous period, a world dominated by dinosaurs on land was equally dominated by a breathtaking inland ocean at its core. This was the Western Interior Seaway, a body of water that did not merely border the continent but completely bisected it, stretching an almost unimaginable distance from the warm waters of the modern-day Gulf of Mexico all the way to the chilly reaches of the Arctic Ocean. If you were to stand today in Denver, Colorado, or Omaha, Nebraska, you would have been standing on the bottom of this sea, under hundreds of feet of water, looking up at a world teeming with life utterly alien to the Great Plains we know. The evidence for this lost world is not hidden away. It is exposed in some of the most iconic and starkly beautiful landscapes on the continent. The multicolored, eroded layers of the Badlands in South Dakota are not just a dramatic spectacle of erosion. They are a literal open book of sedimentary history, each stripe representing millennia of mud and silt that settled gently onto that ancient seafloor. Similarly, the towering chalk cliffs of Kansas, like Monument Rocks and Castle Rock, are made of the compressed microscopic skeletons of countless trillions of tiny marine organisms called coccolithophores that once flourished in the sunlit upper waters of the Seaway. This soft, white rock is the exact same type of limestone that forms the White Cliffs of Dover in England, a testament to a global period of high sea levels. And within these rocks, the fossils tell a story of an ecosystem of staggering diversity and ferocity. This was not a peaceful sea. It was a realm ruled by some of the most formidable predators to ever evolve. The most famous of these were the mosasaurs, gigantic marine lizards that could grow to lengths of over 50 feet. These were not slow, gentle giants, they were the T. Rick says of the ocean, with powerful jaws lined with conical teeth, built for seizing and crushing large prey. Sharing these waters were the long-necked plesiosaurs, whose bizarre body plan, a barrel-shaped torso with 4 flippers, and in some species a neck as long as the rest of its body, allowed them to stealthily ambush schools of fish. The skies above this seaway were patrolled not by gulls, but by pterosaurs like the gigantic Quetzalcoatlus, with a wingspan rivaling a small airplane, which would have soared on the thermals, occasionally dipping down to pluck a fish from the surface. The sea itself was filled with a dizzying array of life, from ammonites with their coiled, chambered shells to giant sea turtles and countless species of fish. The existence of this seaway did more than just provide a home for these creatures. It dramatically influenced the entire continent's climate. Its warm currents would have carried moisture deep inland, creating humid, subtropical conditions on its shores that supported lush coastal forests where dinosaurs like Triceratops and Edmontosaurus thrived before the infamous asteroid impact that would bring this entire world to a sudden and catastrophic end. The sediments laid down on its floor now form the backbone of the continent's geology, and the organic material from all that ancient life, buried and compressed over millions of years, became the vast oil and gas reserves that would later power the modern nations built upon its remains. The Western Interior Seaway is therefore more than a fossil curiosity. It is a foundational chapter in the story of North America, a reminder that the very bedrock of the heartland was formed in the deep, silent darkness of a forgotten ocean. While the Western Interior Seaway was dominating North America, an equally colossal and transformative inland sea was taking shape on the other side of the world, its legacy now written into the very foundations of Europe and Asia. This was the Paratethys Sea, a vast and long-lived body of water that for over 30 million years served as a unique evolutionary laboratory, its eventual disappearance forever altering the climate, geography, and even the course of human history on a continental scale. To understand its immense reach, picture a marine world that began in the alpine regions of what is now Austria and Switzerland, then stretched eastward in a sweeping arc, covering the entire area of the modern-day Pannonian Basin in Hungary, surging around the rising Carpathian Mountains, flooding the lowlands of Romania and Ukraine, and finally spreading out into a truly gigantic basin that now the Black Sea, the Caspian Sea, and the arid plains of Kazakhstan. This was not a simple gulf or a temporary flood. It was a true ocean in its own right, though one that was often isolated from the global ocean system, and that isolation is the key to its incredible story. The evidence for this lost world is astonishingly abundant. Travel through the foothills of the Carpathians or visit the stark landscapes around the Caspian Sea, and you can literally pick up pieces of this ancient seafloor. The ground is strewn with fossilized shells, not just a few, but in some places vast beds of them, layered like pavement. These aren't just any shells, they belong to mollusks that evolved into giant forms, a common evolutionary response in isolated ecosystems where competition is reduced. But the most captivating residents of the Paratethys were its mammals. Cut off from the main oceans, the usual rules of marine evolution were rewritten here. Food sources and habitats were different, leading to the development of species found nowhere else on Earth. The most famous of these were the dwarf whales. Species like the Cetotherium rearbenini, a baleen whale that grew to only about 3 or 4 meters in length, a fraction of the size of its open ocean cousins. This phenomenon, known as insular dwarfism, occurred because the confined space and limited resources of the inland sea placed a premium on smaller body size, which requires less food. The Paratethys was also home to unique species of dolphins, seals, and a bizarre, long-snouted marine mammal known as the sea cow, all evolving on their own peculiar path. The fate of this incredible ecosystem was sealed by the relentless force of plate tectonics. The slow-motion collision of the African and Eurasian plates was like a giant geological vise, gradually squeezing the Paratethys from both the south and the north. This immense pressure did two things. It pushed up mountain ranges like the Alps and the Caucasus, which acted as new walls, and it uplifted the seafloor itself, slowly draining this colossal bathtub. Simultaneously, global climate shifts during the Pliocene epoch caused sea levels to drop, further severing its connections to the world's oceans. The Paratethys didn't just vanish overnight, it went through a dramatic and protracted death. As its outlets to the global ocean closed, it began to evaporate under the sun, becoming increasingly saline. It fractured into a series of large, dying lakes, the direct ancestors of today's Black, Caspian, and Aral seas. In its final stages, it became a hypersaline nightmare, a toxic environment where only the hardiest crustaceans could survive, leaving behind massive deposits of salt and gypsum that are still mined today. The retreat of the Paratethys had profound and lasting consequences. By removing such a massive source of moisture from the heart of Eurasia, the climate of the entire region became significantly drier and more continental. The lush, humid forests that fringed its shores gradually gave way to the vast grasslands or steppes that we see today. This ecological shift was a pivotal moment in human prehistory, as these open plains provided the perfect environment for the evolution of grazing animals and later, the rise of horse-riding nomadic cultures that would dominate the region for millennia. The story of the Paratethys is therefore not just a tale of a lost sea, but a fundamental explanation for the very shape of modern Eurasia, its climate, its resources, and the paths that human civilization would eventually take across its wide, open spaces. But the story of Earth's changing coastlines isn't only written in saltwater. Some of the most dramatic transformations have occurred far from any ocean, in the heart of continents where vast freshwater seas once rose and fell with the rhythms of our planet's climate. To witness this phenomenon on a truly epic scale, we must return to the Sahara, but not to an ancient ocean this time. Instead, we journey to its southern edge, to a place where today we find one of the world's most impoverished lakes, a shallow remnant called Lake Chad. It is almost impossible to believe, looking at its diminished, struggling form, that this was once the center of something monumental. Just a geological blink of an eye ago, during what scientists call the African humid period, this entire region was dominated by Lake Mega Chad, the largest freshwater lake our planet has ever known. Its scale is almost incomprehensible. At its peak around 7,000 years ago, it sprawled over an area of more than 400,000 square kilometers. To put that in perspective, it was larger than the modern Caspian Sea, and it would have completely drowned countries like Germany or Japan. Its shorelines were not confined to a single nation. They stretched across what are now 4 different countries: Nigeria, Niger, Chad, and Cameroon, creating an inland freshwater ocean so vast it would have visibly influenced the local climate, generating its own rain patterns and supporting a world of staggering abundance. The evidence for this lost aquatic giant is not a matter of speculation. It is etched directly into the landscape for those who know how to look. Satellite imagery reveals the ghostly outline of its former extent with stunning clarity, a massive, pale, mineral-rich depression surrounding the modern lake, marking the ancient lakebed. On the ground, the rolling sand dunes of the Sahara slowly encroaching on this basin are not just piles of sand, they are effectively burying a coastline. And if you were to walk across these dunes, you might literally stumble upon the tangible proof. Scattered throughout the sands are the fossilized bones of giant Nile perch, catfish, and tilapia, species that require deep, open water to thrive. Even more poignant are the human artifacts found alongside them: finely crafted stone tools, harpoon points carved from bone, and fragments of pottery. These objects tell a story not of a harsh, barren wasteland, but of a lush, resource-rich paradise that supported thriving communities of early humans. These were not people merely surviving on the edge of existence. They were flourishing, developing sophisticated fishing technologies, and establishing trade networks along these bustling, verdant shores. The existence of Mega Chad is one of the most powerful examples of a climate-driven, green Sahara period. These cycles are triggered by subtle changes in Earth's orbit and tilt, which alter the amount of solar energy received by the continent. During a humid period, monsoon rains that today fall over the ocean are pulled much further north, drenching the Sahara for millennia. This turns the world's greatest desert into a savanna dotted with lakes and crossed by rivers, a perfect habitat for humans and animals alike. Then, as the orbital cycle gradually shifts back, the rains retreat, the lakes evaporate, and the desert reclaims its territory. The story of Lake Mega Chad is therefore far more than a geological curiosity. It is a crucial chapter in the human story. This immense body of water acted as a magnet for life, creating a fertile corridor that enabled some of the most significant migrations in human history. As the climate in other parts of Africa shifted, populations of early humans were drawn to this reliable water source. They settled along its shores, and when the lake eventually began its long, inexorable retreat over thousands of years, it effectively pushed these populations outward, forcing them to adapt and move into new territories, including following the remaining rivers towards the Nile Valley, where some of the world's first great civilizations would eventually take root. This hidden shoreline, now silent and buried, is a profound testament to the fact that the environments we see as permanent and defining are, in the grand scheme of Earth's history, only temporary. Today's deserts were yesterday's hubs of life and activity, and the story of Mega Chad serves as a powerful, humbling reminder of the fragility of water resources and the incredible adaptability of humanity in the face of a constantly changing world. Now, let's turn our attention to one of the most dramatic and catastrophic events in our planet's recent geological history, a story that unfolded not in some remote inland basin, but in one of the world's most famous and familiar bodies of water, the Mediterranean Sea. It is almost impossible to picture this vibrant blue heart of the ancient world, a cradle of civilization and a hub of maritime life, as anything other than what it is today. But roughly 6 million years ago, this entire sea very nearly vanished from the face of the Earth in one of the most spectacular environmental collapses ever discovered. This event is known as the Messinian Salinity Crisis, and its name alone crisis hints at the sheer scale of the catastrophe that unfolded. The cause was deceptively simple, yet its consequences were earth-shattering. The Mediterranean Sea is not an open ocean. It is essentially a giant bathtub with only one major faucet and one major drain, the Strait of Gibraltar, a narrow channel connecting it to the Atlantic Ocean. The entire existence of the sea depends on a delicate balance. Water evaporates from its surface under the hot sun much faster than rain or rivers can replenish it. For millions of years, this balance was maintained because deeper, denser, saltier water from the Atlantic continuously flowed in through the strait to replace what was lost. But then the powerful, relentless force of plate tectonics intervened. The slow-motion collision of the African and Eurasian plates began to push up the seafloor and the land around the Strait of Gibraltar. It was a gradual process, but eventually this geological vise squeezed the connection shut. The Atlantic's life-giving faucet was turned off. Cut off from its source, the Mediterranean began to die. It didn't just slowly shrink, it underwent a violent, rapid desiccation. With the sun's evaporation continuing unabated and no new water coming in, the sea level plummeted at an astonishing rate, perhaps as much as 1 meter every year. Within a few thousand years, a geological blink of an eye, the Mediterranean was reduced to a nightmarish landscape of hyper-salty, toxic brine pools and vast, shimmering deserts of salt under a blistering sun. The water level fell so far that it was not just lower, it was between 1 and 2 miles below the level of the world's oceans. The seafloor was completely exposed, creating a deep, scorching hot, and incredibly salty canyon system that stretched from one end of the basin to the other. The evidence for this apocalyptic event is some of the most striking and bizarre ever found by geologists. Today, if you take a boat into the deepest parts of the Mediterranean and use seismic technology to look beneath the modern seafloor, you will find a layer of salt and other mineral deposits that is up to 2 miles thick in some places. This is the solidified residue of the entire body of water that evaporated, but the clues are even more dramatic on land. The ancient shorelines from this period are not subtle. They are colossal, impossible to miss features. On the islands of Sicily and Cyprus and along the coasts of North Africa, you can find enormous cliffs that were once wave-cut coasts, now stranded high and dry, hundreds of miles from the water. Even more incredible are the fossilized riverbeds. Major rivers like the Nile and the Rhone did not simply empty into a sea, they became something else entirely. With the base level of the Mediterranean dropped by over a mile, these rivers suddenly had a tremendously steep new path to follow. They carved down into the exposed continental shelf with ferocious energy, gouging out deep, dramatic canyons that are breathtaking in their scale. The Nile Canyon, for instance, was cut more than a mile deep and is now completely buried under silt, a hidden ghost of a river's desperate race to reach a vanished sea. The impact of this crisis was felt far beyond the basin itself. The sudden evaporation of such a massive body of water had profound effects on global climate patterns and ocean chemistry. The marine life of the Mediterranean was almost entirely wiped out, creating a biological catastrophe that required the sea to be completely recolonized from the Atlantic when the waters finally returned. And return they did in an event geologists call the Zanclean Flood. As tectonic movements eventually reopened the Strait of Gibraltar, the dam holding back the Atlantic Ocean broke. What followed was quite possibly the largest and most powerful waterfall in the history of our planet. Scientists estimate that ocean water roared through the gap at a rate over 1,000 times greater than the flow of the Amazon River today, refilling the entire Mediterranean basin in a period that may have been as short as 2 years. The roar of that incoming flood would have been audible across continents, and the landscape was transformed once again from a hellish salt flat back into a deep blue sea. The story of the Messinian salinity crisis is the ultimate cautionary tale of geological vulnerability. It demonstrates with terrifying clarity that no body of water, no matter how vast or seemingly permanent, is immune to the powerful and often abrupt forces of our dynamic planet. The Mediterranean Sea, a symbol of stability and permanence for human civilization, was almost erased from the map, leaving behind a stark, salty tombstone that still lies buried beneath its waves. If the previous stories of vanished seas have taught us anything, it's that our planet is a master of transformation, turning seabeds into deserts and coastlines into plains. But perhaps no example of this is more visually staggering, more fundamentally mind-bending than the one we explore next. To truly grasp it, you must perform a mental exercise of epic proportions. Picture the Andes mountain range in South America, those iconic, jagged peaks, the snow-capped volcanoes, the breathtaking altitudes that make your lungs burn. Now imagine all of that not as a towering fortress of rock, but as the bottom of a calm, sun-dappled, ancient Pacific Ocean. This is not a fantasy, it is a geological fact. The very summit of Mount Everest, the highest point on our planet, was once submerged under the Tethys Ocean. But the Andes present a different kind of miracle, not just a single peak, but an entire, vast mountain system, thousands of miles long, that was once entirely underwater. The proof is not buried deep underground. It is literally written in the stones at the top of the world, high in the Andes, at elevations that leave human climbers gasping for oxygen. Paleontologists and geologists have made discoveries that defy all logic of the present. They haven't found just a few scattered shells. They have unearthed entire fossilized reefs, packed with the intricate skeletons of corals that could only have grown in warm, shallow, sunlit seawater. They have found the perfectly preserved impressions of ammonites, those iconic spiral-shelled cephalopods that ruled the ancient seas. They have collected layers of sedimentary rock, sandstone, shale, and limestone, that are identical to those being formed right now on the calm, shallow continental shelves off the coast of Chile and Peru. These rocks and fossils are not found at a modest height. They are routinely discovered at elevations exceeding 3,000 meters, or nearly 10,000 feet, and in some places even higher. Every single one of these fossils, every layer of that water-formed rock, is a silent, unmovable testament to a truth so powerful it recalibrates our understanding of time and geology. The Pacific Ocean once washed over the very spots where condors now soar between mountain peaks. The mechanism behind this incredible change is the single most powerful force shaping our planet's surface, plate tectonics. The story begins during the Mesozoic era, the age of dinosaurs, when the western edge of the South American continent was a passive margin, much like the eastern coast of the United States is today. It was a low-lying, flat landscape, and the Pacific Ocean gently lapped against its shores, depositing those sands and silts and supporting those thriving marine ecosystems. But then, the immense geological engine beneath the crust shifted into a higher gear. The Nazca Oceanic plate began to plunge relentlessly beneath the South American continental plate in a process called subduction. This wasn't a gentle nudge, it was a colossal, slow-motion collision that has continued for tens of millions of years. As the dense oceanic plate was forced downward into the mantle, it created unimaginable pressure and friction, generating the volcanoes that dot the Andes today. But more importantly, it acted like a gigantic bulldozer, slowly, inexorably crumpling the entire western edge of the continent and pushing it skyward. The rate of this uplift is almost beyond comprehension, on the order of several millimeters per year, which over millions of years adds up to thousands of meters. Think of it as a massive elevator carrying an entire ancient coastline on its platform, rising so slowly that no creature living through it would ever notice, but with an end result that is nothing short of monumental. The former seafloor, with all its buried treasures of fossils and sedimentary layers, was simply hoisted up into the thin, cold air, transformed from a watery grave into the spine of a continent. This process is still active today. The Andes are still rising, still being shaped by this titanic struggle between plates. This makes the Andes shoreline more than just a fossil. It is a living, breathing example of the awesome power of plate tectonics. It provides a uniquely clear window into the forces that not only build the world's greatest mountain ranges, but also constantly rewrite the map of our coastlines. It stands as the ultimate symbol of geological change, a stunning, in-your-face reminder that there is no permanent high ground on this dynamic planet. The very rock beneath our feet is in a state of constant, slow-motion flux, and the highest, most solid places on Earth were once the deepest, most fluid realms of all. Leaving behind the towering, ocean-born peaks of the Andes, we now venture into a landscape that feels like the very end of the Earth, the vast, frozen, and seemingly endless expanses of Siberia. This is a land defined by its extreme climate, a place of brutal winters and sparse human presence, where the ground itself remains locked in permafrost for much of the year. It is the last place you might expect to find evidence of a tropical, teeming paradise, and yet that is precisely the secret it holds. If we could peel back the layers of ice and snow and rewind the clock a staggering 400 million years to the Devonian period, we would not be standing on frozen tundra. We would be swimming through a warm, shallow, and incredibly vibrant sea, a marine world so rich and diverse that it has earned a legendary nickname among paleontologists, the Devonian coral reef. This was not a small, isolated body of water. It was a massive inland sea that submerged much of what we now call Siberia, a continent in its own right at the time, located near the equator. The water was clear and sun-drenched, perfect for supporting an explosion of life that would lay the groundwork for the future of our entire planet. The proof of this lost world is not a matter of subtle clues or disputed theories. It is lying in plain sight, preserved with almost miraculous perfection in the remote wilderness. To find it, one must journey to places like the breathtaking Lena River Valley, a UNESCO World Heritage Site where the river has carved magnificent cliffs out of the landscape, exposing layer upon layer of geological history. Within these exposed cliffs, the evidence is overwhelming. The rocks themselves are often a light-colored, fine-grained limestone, a type of rock that forms almost exclusively in calm, warm, shallow marine environments from the accumulated skeletons of countless marine organisms. But the real treasures are the fossils themselves, and they are found in such abundance and quality that it leaves seasoned scientists in a state of awe. You can literally reach out and touch the intricate, segmented shells of trilobites, the hard-bodied arthropods that were the undisputed rulers of the seafloor. These aren't faint impressions, they are often fully three-dimensional, every spine and groove preserved in exquisite detail. Alongside them are the bizarre and formidable armored fish, creatures like the placoderms, which were the first vertebrates to evolve jaws. Some, like the fearsome Dunkleosteus, were true apex predators of their time, but even their smaller relatives found here are encapsulated in stone, their bony head shields and body plates looking as if they were buried just yesterday. And perhaps most telling of all are the fossils of early corals and massive, sponge-like organisms called stromatoporoids. These were the reef builders, the architects of this underwater metropolis. Their fossilized remains form vast, interconnected structures that clearly outline the shape of the original thriving reef ecosystem, a structure that would have rivaled the Great Barrier Reef in its scale and complexity. This Siberian inland sea was far more than just a scenic underwater landscape. It was a crucible of evolution. The Devonian period is often called the Age of Fishes for a reason. It was during this time that fish diversified into almost every ecological niche in the ocean, developing new body plans, new strategies for predation and defense, and setting the stage for the eventual journey of life onto land. The fossils preserved here provide an unparalleled snapshot of this critical evolutionary moment. But the legacy of this sea extends beyond fossils and evolutionary biology. It is also written into the very wealth of the region. Those same limestone formations that entomb the ancient creatures are also the source of immense mineral riches. Over hundreds of millions of years, the organic material from that prolific marine life was buried, heated, and compressed, forming the basis for some of Siberia's vast oil and gas reserves. Furthermore, the sea was a perfect environment for the deposition of other minerals, making the area a geological treasure chest. So, when we study this hidden shoreline, we are doing more than just piecing together an ancient ecosystem. We are connecting the dots between a warm, shallow sea that existed near the equator 400 million years ago and the frozen, resource-rich landmass it became. It demonstrates the deep, fundamental connections between the biology of the past and the geology of the present, revealing how the skeletons of long-extinct creatures can, over eons, become the energy that powers modern civilization. Siberia's frozen wilderness, a symbol of harsh emptiness, is in reality one of the planet's greatest libraries, holding within its stone pages the detailed, beautiful, and violent story of life's first great conquest of the oceans. But the story of Earth's vanished waters doesn't only belong to the distant, deep time past of millions of years ago. Some of its most dramatic and human-relevant chapters were written in a much more recent era, an age when our own species was already beginning to leave its mark on the world. To see this, we travel to the American West, to a region known as the Great Basin. Today, this is a land defined by its stark, dry beauty, a sprawling mosaic of rugged mountain ranges separated by broad, flat valleys, many of which are classic desert, covered in sagebrush and hardy grasses that survive on minimal rainfall. It is a landscape of endurance and scarcity, but this modern reality is a geological illusion, a snapshot from the very end of a much wetter and more dynamic story. If we could step back in time just 20,000 years to the peak of the last ice age, we would witness a scene that would be utterly unrecognizable. Those dry, dusty valleys were not empty. They were filled to the brim with colossal, deep freshwater lakes, forming a complex hydrological system that made this region one of the great water-rich centers of North America. The two most magnificent of these were Lake Bonneville and Lake Lahontan. Lake Bonneville was the giant, a truly inland sea that covered most of western Utah and parts of Nevada and Idaho. At its greatest extent, it was nearly the size of Lake Michigan, a vast blue expanse over 1,000 feet deep in places, its surface agitated by powerful waves driven by ancient storms. Its smaller but still immense sibling, Lake Lahontan, dominated northwestern Nevada, a complex web of interconnected waterways that flooded multiple valleys. The evidence for these vanished giants is not hidden away in scientific journals. It is boldly, visibly etched into the very skin of the landscape for anyone with eyes to see. Drive across the Bonneville salt flats in Utah, that famous, perfectly flat expanse of white that hosts land speed record attempts. You are not driving on a random salt pan. You are driving across the deepest, most central part of the ancient Lake Bonneville lakebed, a place that was once under hundreds of feet of water. Look up towards the surrounding mountains, and you will see the story of the lake's life and death written in lines on the slopes. These are the ancient shorelines, appearing as distinct, horizontal benches or terraces carved into the mountainsides. These are not subtle features. Some are so prominent they look like giant steps for a titan. They were carved by the relentless pounding of waves over thousands of years, and they mark distinct periods when the lake's level stabilized for long periods. The highest of these shorelines, known as the Bonneville shoreline, traces a contour around the entire basin, a ghostly bathtub ring that delineates the lake's maximum possible extent. In Nevada's Black Rock Desert, another vast playa, you can find not just the subtle lines of shorelines but also more tangible evidence. Wave-worn gravel beaches now stranded miles from any water, and piles of tufa rock, a porous limestone that forms underwater around hot springs, standing like strange, silent monuments in the desert, marking where those springs once bubbled up into the deep lake. These lakes were far from barren. Sediment cores pulled from the old lakebeds tell a story of a thriving ecosystem. The waters were rich with fish like cutthroat trout and Lahontan whitefish, whose descendants are now restricted to a few remnant lakes. The shores were lush with vegetation, attracting massive animals like mammoths, giant ground sloths, American camels, and dire wolves. And crucially, this abundance of water and life also attracted some of the earliest human inhabitants of the Americas. Archaeological sites like Nevada's Danger Cave are situated right at the edge of these ancient shorelines. The artifacts found there, fish bones, tools made from water-worn stone, and evidence of lakeside camps prove that human cultures not only witnessed these great lakes but thrived because of them, developing a way of life intricately tied to their resources. So what happened to all that water? The story of their disappearance is a masterclass in climate change. As the last ice age waned, the great continental glaciers to the north began to melt. This might seem like it would add more water to the system, but for the Great Basin it had the opposite effect. The climate patterns shifted. The storm tracks that had been funneling moisture from the Pacific Ocean into the region moved northward. The precipitation that had sustained the lakes for millennia dwindled, switching from a steady input to a trickle. Meanwhile, the fierce desert sun continued to evaporate the vast water surfaces. The balance was broken. The lakes began a long, inexorable retreat, shrinking faster than any river or rain could replenish them. Their death was not quiet. Lake Bonneville's demise was particularly dramatic. As it overflowed its basin at Red Rock Pass in Idaho, it triggered a catastrophic flood of biblical proportions, unleashing a wall of water that scoured the landscape of southern Idaho and raced towards the Pacific Ocean, an event that permanently altered the geography of an entire region before the lake settled back into a slower evaporation. Today, all that remains of these titans are their salty, shrunken ghosts. The Great Salt Lake is a tiny, hypersaline remnant of Lake Bonneville, and Pyramid Lake in Nevada is a small, precious leftover of Lake Lahontan. Scientists study these ancient shorelines with intense interest, and not just to understand the past. These fossil coastlines provide critical data points for climate models. By understanding exactly how much water was in these lakes, how quickly they rose and fell, and what specific climate shifts caused those changes, researchers can better predict how modern water resources in the arid West will respond to our current period of global warming. The story of the Great Basin's Pleistocene lakes is a powerful and sobering lesson in hydrological fragility. It demonstrates with stunning clarity that a water-rich environment is not a permanent guarantee, but a delicate equilibrium that can be overturned by relatively subtle shifts in the climate, leaving behind a stark and beautiful monument to what was lost. From the vast, evaporated lake beds of the American West, we now journey to a desert of an entirely different scale and character, a place so immense and inhospitable that its very name declares its emptiness. The Rub al-Khali, or the Empty Quarter, sprawls across the southern Arabian Peninsula, a seemingly infinite ocean of sand dunes, the largest continuous sand desert on Earth. Here the sun reigns supreme, temperatures soar to blistering heights, and the landscape appears as a timeless, barren wilderness, utterly devoid of water and life. But this is one of geology's greatest deceptions. Beneath those towering, shifting dunes lies the ghost of a vibrant, watery world, a coastline that whispers of a time when the Indian Ocean did not stop at the peninsula's edge but poured deep into its heart. This transformation occurred during the Miocene epoch, a period of significant global change roughly 20 million years ago. At that time, the world was warmer and sea levels were substantially higher. The tectonic plates that cradled the Arabian Peninsula were also shifting, causing the land to subside in certain areas and creating a vast, low-lying basin that was an open invitation to the sea. The Indian Ocean answered that call, flooding inland to create a shallow, warm, and sun-drenched embayment that would have looked more like the modern-day Persian Gulf than the harshest desert on the planet. The evidence for this incredible incursion is not buried in some inaccessible, remote canyon. It is scattered throughout the sand sea itself, waiting to be uncovered by the wind or by the careful hands of geologists. Prospectors and scientists exploring the Empty Quarter have made discoveries that seem to belong to another world entirely. They have found not sand-smoothed stones, but the intricate, fossilized skeletons of entire coral reefs, their delicate structures preserved in minute detail. These corals could only have grown in clear, shallow, saline water, proof positive of a thriving marine ecosystem. Alongside them are the fossilized roots and pneumatophores of mangrove trees, species that grow in the intertidal zone where land meets sea. Finding these remains in the deepest, driest part of the desert is a paradox that forces a complete reimagining of the landscape's entire history. Even the sand itself tells a story. Core samples reveal layers of fine marine sediments, clays, and silts that settled gently on a calm seafloor, now sandwiched between immense layers of wind-blown sand. This ancient shoreline is far more than a fascinating geological oddity. It is a critical key to understanding the modern Middle East. The same tectonic forces that lowered the land to allow the ocean in also helped create the geological structures that would later trap one of the world's most valuable resources, oil. The warm, shallow Miocene Sea was a perfect biological factory. Countless trillions of microscopic plankton and algae thrived in its sunlit waters. When they died, their organic remains settled into the oxygen-poor mud on the seafloor, preventing them from fully decomposing. Over millions of years, this organic sludge was buried under thicker and thicker layers of sediment. The immense heat and pressure from this burial cooked the organic matter, slowly transforming it into the hydrocarbons that make up crude oil and natural gas. The porous rocks of the former seafloor and shoreline, like limestone and sandstone, became the reservoirs, while layers of impermeable rock acted as seals, trapping the oil in place. Therefore, the very same environment that left behind fossilized corals and mangroves also provided the fundamental ingredients for the petroleum wealth that would define the region in the modern era. The Rub al-Khali's hidden coastline is a profound lesson in the deep connections between past environments and present-day resources. It reveals that the stark, oil-rich deserts of the Arabian Peninsula are not a static, eternal reality, but merely the current chapter in a long story of dramatic change, a story written in fossils and fuel, where the paths of ancient ocean currents ultimately dictated the flow of modern global commerce. Leaving behind the vast, recent lakes of the American West and the oil-rich deserts of Arabia, our journey now takes us to the very end of the world, to a land of raw, elemental power and breathtaking beauty, Patagonia. Stretching across the southern tips of Argentina and Chile, this is a region defined by its extremes, towering, glacier-clad peaks, fierce winds that scream across open steppes, and coastlines where the Atlantic and Pacific Oceans clash with untamed fury. It feels like a primordial landscape, a place that has always been wild and untouched. But that impression, like so many others we've encountered, is a magnificent illusion. Patagonia is not a static monument to wilderness. It is a grand, open book of geological change, its pages written in stone and fossil, telling a complex story of oceans that repeatedly claimed this land for their own. Unlike many of the shorelines we've explored, which were shaped by a single, dominant event, Patagonia's history is one of layered invasions. This wasn't just one ocean coming in one time. This was a protracted dance between land and water, with the Atlantic and Pacific taking turns flooding the continent due to two powerful forces working in tandem. First, there was tectonic subsidence. The immense weight of the rising Andes Mountains to the west literally pressed down on the continent's edge, causing the land east of the mountains to sag and buckle, creating a vast, low-lying basin just begging to be flooded. Second, there were periods of globally high sea levels, particularly during warm intervals between ice ages, when melting polar ice poured water back into the ocean basins, causing the seas to rise and spill over into these waiting depressions. The evidence for these repeated marine incursions is not hidden away. It is spectacularly exposed in the stark Patagonian landscape. In the badlands of Argentine Patagonia, paleontologists have made finds that are both breathtaking and bizarre. The complete, articulated skeletons of ancient whales lying in silent repose on the dry, scrub-covered plains, dozens of miles from the crashing waves of the modern Atlantic coast. These are not just isolated bones, they are entire animals preserved where they died on a seafloor that vanished millions of years ago. Alongside them are vast fossilized shellfish beds, enormous congregations of clams and oysters that once thrived in these shallow, nutrient-rich waters, their shells now cemented together into solid rock that erodes out of the cliffs in a continuous, gleaming white ribbon. And perhaps most visually striking of all are the marine terraces. Along the coasts of Chile, you can see a series of these perfectly flat, Chinese letter-like benches carved into the hillsides, rising one after another like a giant staircase leading away from the ocean. Each of these terraces represents a former coastline, a moment in time when the sea level was stable long enough for waves to carve a lasting mark into the rock before either rising higher or retreating once more. This layered history makes Patagonia a unique laboratory for understanding the entire geological story of South America. The story of these shorelines is inextricably linked to the titanic forces that built the Andes Mountains. As the Pacific Oceanic plate relentlessly pushed beneath the continent, it not only thrust the mountains skyward but also caused the dramatic subsidence that allowed the oceans to flood in from the east. Furthermore, the final separation of South America from Antarctica, which opened the deep, powerful current of the Drake Passage, had a profound impact on global climate and ocean circulation patterns, which in turn influenced the timing and extent of these sea level changes that washed over Patagonia. But beyond just telling us about the past, these ancient Patagonian shores hold a critical mirror up to our present and future. By studying the fossilized ecosystems within these rocks, seeing which species thrived and which went extinct as the oceans advanced and retreated, scientists can observe how marine life responded to rapid environmental changes in the past. This provides a crucial deep-time analog for understanding how modern ocean ecosystems might respond to the sea level rise and ocean acidification driven by our current period of climate change. The whales stranded in the desert and the oyster beds on the mountainside are more than just curiosities. They are a stark and powerful testament to the incredible dynamism of our planet. Patagonia, in all its wild and rugged grandeur, does not represent a timeless wilderness, but rather a landscape that has been continuously remade by the powerful, intertwined forces of geology and climate, a perpetual negotiation between the solid earth and the restless sea. Now we journey to a geological paradox, a place where two of the most destructive and creative forces on our planet, fire and water, engaged in a spectacular, simultaneous dance of construction and obliteration. We travel to India, to the vast stepped mountains of the Deccan Plateau. This is a landscape forged in the deepest furnaces of the earth, a region dominated by the Deccan Traps, one of the largest volcanic features on the planet. Here, the ground is composed of layer upon layer of dark, solidified basalt lava, a testament to apocalyptic eruptions that once spewed enough molten rock to bury entire countries. It is a place that feels fundamentally, primordially fiery, and yet hidden within these layers of ancient fire is the unmistakable, quiet signature of water. For during those same cataclysmic events, shallow seas repeatedly washed over this land, leaving behind a geological record so unique it helps us unravel one of the greatest mysteries in Earth's history. The story takes us back to the very end of the Cretaceous period, around 66 million years ago. India was not where it is today. It was a massive island continent, adrift in the Indian Ocean on its own tectonic plate, slowly but surely making its way northward to its eventual collision with Asia. As it drifted, it passed over a deep-seated, stationary hotspot of magma, a geological blowtorch that began to burn through the crust from below. This triggered one of the most prolonged and voluminous series of volcanic eruptions the world has ever seen. For hundreds of thousands of years, the Deccan Traps volcanoes gushed unimaginable quantities of lava, covering the landscape in a series of massive flows, each one potentially dozens of meters thick. But the land these floods of fire were consuming wasn't a barren, rocky plain. At the time, much of it was actually submerged under a warm, shallow sea. Global sea levels were exceptionally high, and the low-lying parts of the drifting Indian continent were inundated. This set the stage for an incredible back and forth between these two elemental forces. A volcanic episode would erupt, pouring incandescent lava across the seafloor, instantly boiling the water and annihilating any life in its path. The lava would cool rapidly upon contact with the water, often forming distinctive pillow-like shapes. Then, as the volcanic activity paused for a period, perhaps centuries or millennia, the ocean would calmly reclaim the territory. Sediments would settle on top of the newly cooled, black lava flow. Life would cautiously return. Clams would burrow into the new seabed, microscopic plankton would die and rain down their tiny skeletons, and the gentle currents would distribute sand and silt, creating a new layer of normal marine rock. Then the fires would break out again. Another titanic lava flow would surge out, burying that new seafloor and all its fossils under another thick layer of basalt, and the cycle would begin anew. The proof of this incredible interplay is found in the very cliffs of the Deccan Plateau. Geologists examining these layered sequences don't just see endless, monotonous dark rock. They see distinct light-colored bands sandwiched between the basalt. These are the fossilized remains of those ancient seafloors. Within these delicate layers, they find the evidence of the life that briefly flourished between the eruptions, the fossilized shells of clams and oysters, the tiny, intricate skeletons of single-celled marine organisms called foraminifera, and even the bones of marine reptiles. These fossil-rich layers are like the pages of a book, meticulously recording the periods of peaceful marine life that were so abruptly and repeatedly interrupted by catastrophic fire from below. This makes the Deccan shoreline uniquely important because its story is locked in time with one of the most famous events in Earth's history, the mass extinction that wiped out the dinosaurs and 75% of all life on the planet. For decades, the leading theory pointed to a single, sudden cause, the massive asteroid impact in present-day Mexico that created the Chicxulub crater. But the detailed record preserved in the Deccan traps tells a more complex story. It suggests that the world was already under immense stress. The prolonged volcanic activity was pumping enormous quantities of volcanic gases, sulfur dioxide, carbon dioxide, and aerosols into the atmosphere for hundreds of thousands of years. This would have caused drastic climate swings, from violent volcanic winters that blocked out the sun to intense periods of global warming, acidifying the oceans and severely disrupting ecosystems worldwide. The dinosaurs and other creatures were likely already in a state of decline, struggling to adapt to a world becoming increasingly hostile. The asteroid impact, then, was not necessarily a lone assassin, but perhaps a final knockout blow to a world already on the ropes. The Deccan traps, therefore, offer a terrifyingly profound lesson. They show us that the most dramatic turning points in our planet's history are rarely caused by a single, simple event. Instead, they are often the result of a perfect storm of catastrophes, a synergy of disasters where the combined effect is far greater than the sum of its parts. The shoreline fossils trapped between those lava flows are silent witnesses to this duality. They speak of both the resilience of life, constantly trying to rebound, and the overwhelming power of the planet to reset the conditions for that life in the most violent ways imaginable. India's geological history is not just a tale of volcanic fire or marine incursion. It is a stark, layered narrative of how the world can change, written in the alternating pages of stone and fossil, a chronicle of chaos that ended one world and made room for the next. Now, we venture into one of the most enigmatic and vital landscapes on our planet, the Congo River Basin. This is the heart of Africa, a place of profound mystery and immense scale, home to the world's second-largest rainforest, a sprawling, green labyrinth teeming with life and carved by the powerful, snaking flow of the Congo River. It is a realm defined by freshwater, by humidity, by the constant drip of rain and the roar of massive waterfalls. It feels like the most terrestrial place imaginable. And that is what makes its deepest secret so astonishing. For beneath that unimaginable weight of vegetation, beneath the layers of mud and soil carried by the river for millennia, lies irrefutable evidence that this entire, vast interior was once not a river basin at all, but an extension of the Atlantic Ocean. This incredible story begins during the Cretaceous period, the golden age of dinosaurs, a time when global sea levels were at some of their highest points in Earth's history. The supercontinent of Pangaea was still in the process of breaking apart, and the South Atlantic Ocean was a relatively new and widening feature. As the continents of Africa and South America drifted slowly away from each other, the crust along their margins was stretched and thinned. This created a vast, low-lying topographic depression along the western edge of what is now Central Africa, a massive, sunken bowl just waiting to be filled. The Atlantic Ocean, seizing the opportunity, poured in. This was not a gentle flooding of a coastline, it was a full-scale marine invasion. The ocean pushed eastward, creating a massive, shallow seaway that extended hundreds of miles into the continent, submerging much of the area that would one day become the Congo Basin. For millions of years, this was not a rainforest but a warm, shallow sea, its waters likely similar to the modern-day Caribbean, lapping against shores that are now buried deep in the continental interior. The proof of this oceanic past is not found on the surface. It is locked away, accessed only by the deep cores drilled by geologists and the occasional glimpse offered by riverbank erosion. Within those core samples, scientists have found layers of sedimentary rock that are utterly out of place for a river basin. There are deposits of fine-grained marine mudstones and siltstones, the kind that only form in the calm, deep waters of a continental shelf. Even more definitive are the fossils. Embedded within these rocks are the undeniable remains of saltwater life, the microscopic skeletons of planktonic foraminifera that drifted in the open ocean, the fossilized shells of ancient clams that lived on the seafloor, and even the teeth of marine sharks. Finding these relics so far from any modern coast is like discovering a message in a bottle that has been buried for 100 million years, a message that completely rewrites the history of this iconic landscape. The legacy of this ancient sea is not confined to the rocks. It has fundamentally shaped the Congo we know today. When the ocean eventually retreated, driven by further tectonic adjustments that raised the land and by falling global sea levels, it left behind a transformed world. The massive depression it carved out became the perfect receptacle for the Congo River system. The river's entire sprawling network of tributaries and its complex drainage patterns were essentially inherited from this sunken, pre-formed basin. Furthermore, scientists hypothesize that this period of marine incursion had a profound impact on the region's legendary biodiversity. The retreating ocean would have left behind a mosaic of new habitats and isolated pockets of life, creating unique evolutionary pressures. Some researchers speculate that certain species found in the Congo Basin today may have ancestors that were originally marine or coastal creatures that adapted to a new life in freshwater as the sea drained away, contributing to the incredible web of life that makes the rainforest so unique. Studying these buried shoreline deposits is about more than just satisfying geological curiosity. It provides a critical window into Earth's deeper climatic rhythms. The chemical composition of the marine sediments and the types of fossils found within them act as an ancient climate proxy. They can tell scientists about the temperature of the ocean water, the strength of long-vanished currents, and the overall climatic conditions of the Cretaceous period, a time when the planet was a much warmer greenhouse world. This data is invaluable for building accurate models of past climate change, which in turn helps us understand the potential trajectories of our own warming planet. The Congo Basin's hidden marine past, therefore, stands as a powerful testament to the incredible dynamism of the African continent. It shatters the illusion of permanence, revealing that even the most seemingly stable and immense landscapes are merely temporary features on a planet that is in a constant, slow-motion state of flux. The mighty Congo River, a symbol of terrestrial power, flows over a foundation built by the ocean, a permanent reminder that the boundaries between land and sea are, and always have been, negotiable. Now we ascend to the very roof of the world, to a landscape that seems to defy the very possibility of an ocean, the immense, wind-swept Tibetan Plateau, and the jagged, sky-piercing pinnacles of the Himalayas. This is the highest place on Earth, a realm of thin, cold air where the horizon is dominated by snow-capped peaks and the ground feels ancient and eternal. It is the last place you would ever imagine finding a seashell, and that is precisely what makes the truth so profoundly staggering. Every single step taken across this high-altitude wilderness is a step upon what was once the deep, dark floor of a vanished ocean. The story of this shoreline begins not with a single event, but with the epic, billion-year saga of continental drift. Picture a world before the Himalayas existed, when the supercontinents of Laurasia in the north and Gondwana in the south were separated by a vast, wide, and deep body of water known as the Tethys Ocean. This was no minor sea, it was a dominant feature of the ancient planet, its waters separating the landmasses that would one day become the familiar continents we know. For eons, the Tethys was a world of its own, its depths teeming with life, its calm abyssal plains steadily accumulating layer upon layer of sediment, the skeletons of countless marine organisms, fine silt and sand that gently rained down from above. This was the quiet, peaceful prelude to the most colossal collision in Earth's history. The evidence for this oceanic past is not a matter of subtle inference. It is bold, undeniable, and literally underfoot. The proof is written in the very rocks that form these mighty mountains. The summit pyramid of Mount Everest itself is not made of a typical volcanic or granite rock. It is composed of a pale, layered limestone. And this is no ordinary limestone. It is packed with the fossilized remains of crinoids, brachiopods, and other sea creatures that lived and died in the warm, shallow waters of the Tethys Ocean over 400 million years ago. To stand at the base of Everest and look up is to gaze upon a former seabed that has been lifted to an altitude of over 29,000 feet. This is perhaps the most powerful single image in all of geology. But the clues are everywhere. Across the high passes of Tibet, geologists routinely find ammonites, those iconic spiral-shelled cephalopods, frozen in stone at elevations that leave humans breathless. These fossils are not rare curiosities. They are abundant, undeniable markers that this entire region was once a thriving marine ecosystem. The mechanism behind this incredible transformation is the relentless, unimaginably powerful force of plate tectonics. The story of the Himalayas is the story of a slow-motion, continent-scale car crash. The Indian subcontinent, once a part of Gondwana, broke away and began its own northward journey across the Tethys Ocean, riding on its own tectonic plate. For millions of years, it raced towards Asia at a rate of several inches per year, a blistering speed in geological terms. When it finally slammed into the southern underbelly of Asia, the results were cataclysmic. The Tethys Ocean, which had separated them, had nowhere to go. Its dense oceanic crust was forced downward and swallowed into the mantle in a process called subduction. But the immense pile of soft sediments that had accumulated on its floor, those layers of limestone and fossil-rich mud, could not be subducted. Instead, they were caught in the middle, scraped off the descending plate and crumpled, folded, and thrust violently upward. It was like pushing two pieces of paper together on a table. The edges buckle and rise into a ridge. In this case, the ridge is the entire Himalayan mountain range and the Tibetan plateau behind it. The force of the collision was so immense that it didn't just create mountains. It thickened the entire crust to an extraordinary degree, pushing what was once seafloor to the top of the world. This process did not happen in a geological instant. It is ongoing. India is still plowing into Asia, and the Himalayas are still rising at a rate of about 1 centimeter per year, continuously pushing those ancient marine fossils ever higher. The significance of this shoreline extends far beyond a fascinating history lesson. The creation of the Tibetan Plateau, this massive block of rock now 3 miles above sea level, has had a profound and direct impact on the global climate. It acts as a gigantic barrier to atmospheric circulation, disrupting wind patterns and playing a fundamental role in creating the monsoon systems that bring seasonal rains to billions of people across Asia. The uplift of these rocks also accelerates chemical weathering, a process that pulls carbon dioxide out of the atmosphere and has contributed to the long-term cooling of the planet. Therefore, the ghost of the Tethys Ocean, preserved in the summit of Everest, is not just a relic, it is an active participant in shaping our modern world's climate and weather patterns. It is the ultimate symbol of planetary change, a breathtaking demonstration that the ground beneath our feet is not permanent, but is instead a page in a dynamic, ever-changing story written by the movement of the continents themselves. But the story of coastlines lost to the sea is not confined to the distant, geological deep time of millions of years ago. Some of the most recent and personally resonant chapters were written in an era when our own species was already beginning to shape the world. To discover this, we must look not to a desert or a mountain range, but to the cold, grey waters of the North Sea between the United Kingdom and the Netherlands. Today, this is a notoriously rough and treacherous body of water, a place of powerful currents, frequent storms, and busy shipping lanes. But if we could drain away those waves and peer at the seafloor, we would not see a barren, sandy plain. We would see the ghost of a lost world, a vast, low-lying landscape of gentle hills, meandering rivers, fertile valleys, and dense forests. This was Doggerland, and for thousands of years it was not a sea, but the very heartland of Mesolithic Europe. During the peak of the last ice age, so much of the planet's water was locked away in colossal ice sheets that global sea levels were over 100 meters lower than they are today. The North Sea, being relatively shallow, was completely exposed. This was not a minor land bridge. It was a sprawling, habitable territory, an area larger than the modern United Kingdom that seamlessly connected the British Peninsula to the European mainland. It was a rich and inviting environment, a mosaic of ecosystems that supported an incredible abundance of life. Herds of giant elk, aurochs, and red deer roamed its open woodlands and grasslands. Rivers thrived with fish, and the coastal marshes and lagoons were teeming with waterfowl and shellfish. And into this paradise came humans. These were not crude cavemen. They were sophisticated hunter-gatherers of the Mesolithic period, with complex social structures, advanced tool-making skills, and a deep understanding of their environment. They established seasonal camps along the rivers and lakes, hunted the great beasts of the plains, gathered nuts and berries from the forests, and harvested the bounty of the wetlands. Doggerland was not a peripheral territory. For these people, it was the center of their world, a thriving, connected continent that allowed for the exchange of ideas, resources, and genes across a wide area. The evidence for this lost civilization does not come from grand, sunken cities. It comes from the patient, meticulous work of marine archaeologists and the occasional, miraculous finds of fishermen trawling the seabed. For decades, fishing boats dragging their nets across the bottom of the North Sea have been hauling up more than just cod and plaice. They have brought up the tangible, poignant remnants of Doggerland, the perfectly preserved antler of a giant elk, still showing the cut marks from a stone tool where a hunter began to work it into a harpoon point. They have recovered the jawbone of an aurochs, the massive, extinct wild ox. Most incredibly, they have found human artifacts, exquisitely crafted flint arrowheads, barbed bone points for fishing, and even fragments of primitive rope. These objects are not water-worn and ancient-looking. Many are in such pristine condition that they look like they were dropped just yesterday, a chilling testament to how suddenly this world was taken away. The end of Doggerland was not a single catastrophic event, but a protracted and inexorable tragedy driven by the same forces we face today: climate change and rising sea levels. As the last ice age waned, the great glaciers began to melt, pouring immense volumes of water back into the world's oceans. The sea began a slow, relentless advance, creeping into the low-lying valleys of Doggerland. The people living there would have witnessed their world shrinking year by year. Forests that once provided hunting grounds would have become salt marshes and then submerged entirely. Familiar rivers swelled and flooded, their estuaries widening into impassable channels. The rich hunting grounds were fragmented and resources became scarcer. This was not a passive drowning, it was an active, forced migration. Communities were pushed relentlessly westward towards the higher ground of Britain and eastward towards the European mainland, compressing populations and likely creating conflict over diminishing territory. The final death blow may have been delivered by a natural disaster. Around 6,200 years ago, a massive submarine landslide off the coast of Norway, known as the Storegga Slide, triggered a colossal tsunami that would have roared across the remaining low-lying plains of Doggerland. For the few communities still clinging to this drowning world, this wall of water would have been apocalyptic, scouring the landscape and delivering the coup de grace to a land already on the brink of disappearance. Shortly after, the seas closed over the last hills and Doggerland vanished forever beneath the waves. The story of this lost landscape is far more than an archaeological curiosity. It is a deeply human story of displacement and adaptation in the face of environmental catastrophe. It provides us with a powerful, prehistoric parallel to the challenges faced by coastal communities today. The inhabitants of Doggerland were among the world's first climate refugees, forced to abandon their homes and traditions by a changing world they could not control. Studying their story through the fragments recovered from the seabed gives us profound insights into how human societies respond to such existential threats: the migrations, the cultural shifts, the innovations born of necessity. Doggerland's drowned shores stand as a silent, sobering monument to the fact that the coastlines we consider permanent are anything but, and that the rising seas of our own era have the power to rewrite human geography once again, erasing not just land, but the entire histories of the people who called it home. Antarctica today stands as a frozen fortress, a continent encased in ice so thick it grinds entire mountain ranges beneath its weight and defines our very concept of absolute cold. It feels like a planet unto itself, a permanent, sterile, and lifeless expanse. But to truly understand this icy giant, we must journey to one of its most bizarre and contradictory landscapes, the McMurdo Dry Valleys. This is a place that defies all logic. Nestled between towering glaciers, these valleys are completely free of ice. They are a polar desert, one of the driest places on Earth, where the air is so arid that snow evaporates before it can even touch the ground, and the rocky soil is so cold and sterile that it is considered the closest analog on our planet to the surface of Mars. It is here, in this seemingly dead and alien environment, that we find one of the most compelling and poignant clues to Antarctica's lost world. Scattered across the valley floors and carved into the surrounding slopes are the undeniable signs of a vibrant, liquid past. The most striking features are the raised beaches. These are not sandy stretches you might find on a tropical holiday. They are ancient, wave-cut terraces and lines of water-worn gravel that now sit high and dry, stranded dozens of meters above the current valley floors. They form distinct horizontal lines on the hillsides like bathtub rings from a vanished ocean, marking precise moments in deep time when the water level was stable. Even more astonishing than these geological features are the biological ones. Embedded in the sedimentary rocks of these dry valleys, paleontologists have discovered the fossilized remains of marine life. We are not talking about a few scattered shells. We are talking about the intricate skeletons of diatoms, microscopic algae that form the base of the marine food web, and the remains of larger marine organisms that could only have thrived in open, liquid seawater. Finding the ghosts of plankton in the driest desert on Earth is a paradox of the highest order, and it points to a single, inescapable conclusion. Millions of years ago, during periods of much warmer global climate, the massive East Antarctic ice sheet that now dominates the continent had significantly retreated. Without that colossal weight of ice pressing down, the land itself actually rebounded upward in a process called isostatic uplift. This combination of less ice and higher land allowed the ocean to flood deep into these valley systems, transforming them from frozen wastelands into sheltered, ice-free fjords, similar to those found in Norway or New Zealand today. These would have been calm, protected inlets, their waters rich with nutrients and life, surrounded by barren but ice-free land. The climate would have been cool, perhaps similar to that of modern-day Iceland or Patagonia, but far from the deep freeze we see now. This evidence is absolutely vital for scientists trying to piece together the puzzle of Antarctica's dramatic transformation. By dating the fossils and the ancient beach deposits, they can create a timeline of when these valleys were flooded, and by extension, when the great ice sheets advanced and retreated. This history is crucial because Antarctica is not just a passive participant in Earth's climate system. It is a powerful driver of it. The formation of its massive ice sheets locked away enormous volumes of the world's water, lowering global sea levels and altering ocean currents that distribute heat around the planet. Understanding how and when this happened helps us comprehend the fundamental mechanics of our entire global climate engine. But the relevance of these dry valley shorelines is not confined to the past. They offer a terrifyingly clear window into our potential future. The conditions that allowed the ocean to flood these valleys, a warmer planet with significantly less polar ice, are the very conditions we are currently creating through the release of greenhouse gases. Scientists study these ancient sediments and fossils as a natural laboratory, a real-world example of what a warmer world looks like. They can analyze how quickly the ice retreated, how far the seas advanced, and how the ecosystems responded. This data is then fed into sophisticated computer models to improve our predictions of how the modern ice sheets of Greenland and Antarctica will behave as global temperatures continue to rise. The silent, frozen shores of the McMurdo Dry Valleys are therefore more than just a geological curiosity. They are a prophetic landscape. They stand as a stark and sobering warning, a physical demonstration that the Antarctic ice cap is not a permanent, immutable feature of our planet. It has changed before, and the evidence suggests it can change again, with consequences for sea level rise that would reshape every coastline on Earth. This hidden coastline reveals that the most extreme and seemingly eternal environments are often the most fragile, holding within their rocks the secrets of both past worlds and the world that may be to come. Our journey now takes us from the frozen prophecies of Antarctica to the sun-drenched, vibrant heart of South America, to the Brazilian highlands. This is a landscape of dramatic plateaus, deep river valleys, and rolling hills that form the backbone of eastern Brazil, a region famous for its coffee plantations and sprawling cities like Sao Paulo and Rio de Janeiro. It feels quintessentially, inarguably terrestrial, a world defined by its elevation and its distance from the ocean. Yet this elevated fortress holds a secret that seems to defy its very identity. For woven into the very rock of these highlands, sometimes over 1,000 meters above the modern sea, is the indelible proof that the mighty Atlantic Ocean once claimed this land as its own. This story doesn't begin with a simple flood or a temporary sea level rise. It is tied to one of the most fundamental and dramatic events in our planet's history, the violent, messy, and magnificent breakup of the supercontinent Gondwana. Imagine a world around 130 million years ago during the early Cretaceous period. The great southern landmass of Gondwana, a colossal amalgamation of what would become South America, Africa, Antarctica, Australia, and India, was beginning to tear itself apart. Deep beneath the surface, immense plumes of hot mantle rock were welling up, stretching and thinning the continental crust like warm taffy. As this stretching continued, the land began to sag, creating a massive, low-lying rift valley that ran along the zone of weakness between the future South America and Africa. This was not a small crack, it was a continental-scale wound, a precursor to an entire ocean. And into this deepening depression, the waters of the ancient southern oceans began to pour, creating a narrow but rapidly widening seaway. For millions of years, as the continents continued their slow, inexorable divorce, this new-born Atlantic Ocean repeatedly flooded deep into the interior of the fracturing landmasses. The Brazilian highlands, which today stand so proud and far from the coast, were at that time the eroded, sloping shoulders of this new ocean basin. The evidence for this is not a matter of theoretical models. It is physical, tangible, and scattered across the interior. Geologists exploring the highlands have uncovered layers of sedimentary rock that are utterly out of place for an upland environment. There are fine-grained shales and mudstones that could only have been deposited in the calm, deep, quiet waters of a continental shelf. Even more definitive are the fossils. In quarries and road cuts far from the coast, researchers have found the unmistakable remains of ancient marine life. The fossilized shells of oysters and other bivalves that lived on the seafloor, the tiny, intricate skeletons of planktonic foraminifera that drifted in the water column, and the teeth of marine sharks. Finding these oceanic relics so high up and so far inland is a discovery that permanently alters our perception of this landscape, revealing it not as a permanent high ground, but as a former seabed that has been lifted up and exposed by the very tectonic forces that created it. The legacy of this ancient shoreline is far more than a fascinating geological anecdote. It is fundamentally written into the wealth and structure of modern Brazil. The same processes that created the Rift Valley and allowed the ocean to flood in also set the stage for the formation of some of the country's most vital natural resources. Those deep marine sediments, rich with the organic material from that ancient sea, were buried, heated, and compressed over millions of years. This process slowly cooked that organic matter, transforming it into the vast offshore oil reserves that today lie beneath the Atlantic Ocean off the coast of Brazil. But the influence doesn't stop at the coast. The tectonic stretching that preceded the continental breakup also created faults and fractures in the crust deep beneath the highlands. These fractures acted as plumbing systems, channeling mineral-rich hydrothermal fluids from deep within the earth. As these fluids cooled, they deposited their dissolved minerals, forming some of the world's largest and most valuable deposits of precious metals and gems. The famous iron ore of Minas Gerais, which forms the backbone of Brazil's mining industry, and the stunning aquamarines and emeralds found in the region, are all a direct, if distant, consequence of those same tectonic forces that first invited the ocean inland. Furthermore, this marine chapter played a crucial role in shaping the region's astounding biodiversity. When the ocean eventually retreated for the last time, driven by the continued widening of the Atlantic and global sea level changes, it left behind a transformed landscape. The sediments deposited by the sea weathered into exceptionally nutrient-rich soils that now support the incredibly diverse Cerrado savanna ecosystem, one of the world's biodiversity hotspots. The unique evolutionary paths of many species found here may have been influenced by the isolation and new habitats created by the retreating waters. Therefore, the story of Brazil's hidden shoreline is a masterclass in the deep, interconnected nature of our planet. It shows us that the forces that build continents and oceans are the very same forces that create the resources upon which civilizations are built and that shape the environments that nurture life's incredible variety. The Brazilian highlands, a symbol of solid, unshakable land, stand as a monumental testament to the fact that our world is a single, integrated system, where the ghosts of ancient seas continue to shape the destiny of the lands they once abandoned. But to truly grasp the immense age of our planet, to feel the weight of billions of years of history, we must now journey to a place that forms the very foundation of the North American continent, the Canadian Shield. This is not a landscape of dramatic young mountains or soft, sedimentary plains. This is something far older, far more primordial. Imagine a vast, sprawling expanse of ancient, exposed bedrock, scraped clean by glaciers, dotted with countless lakes, and covered in a thin skin of boreal forest. This is the Shield, a geological titan that covers nearly half of Canada and stretches into the northern United States. Its rocks are not mere millions of years old. They are billions of years old, representing some of the most ancient crust on the face of our planet. To walk across this rugged terrain is to walk directly on the raw, unvarnished heart of the continent, a place that feels eternal and unchanging. And yet, even here, in this most ancient of places, the ocean has left its indelible, repeated mark. The story of the Shield's shorelines is not a single chapter, but an entire volume written over an almost incomprehensible span of time. For much of its multi-billion-year history, this stable core of the continent, known as a craton, was not high and dry. It was repeatedly submerged by warm, shallow, epicontinental seas that washed over its low-lying surface. These were not the deep, wild oceans we know today, but vast, calm, sun-drenched lagoons that would have stretched from horizon to horizon. The proof of these long-vanished waters is not found in dramatic sea cliffs or wave-cut terraces. Those features were erased eons ago. Instead, the evidence is locked within the rocks themselves, in the most subtle and yet most profound ways imaginable. In areas like Ontario and Quebec, interspersed amongst the ancient igneous and metamorphic rocks, you find bands of sedimentary stone, limestone, dolostone, and shale. These layers are the lithified mud and silt that settled gently onto those ancient seafloors, and within these stones you find the true treasure, fossils. But these are not the fossils of dinosaurs or giant reptiles. These are the fossils of Earth's earliest, most primitive life. The most spectacular examples are stromatolites. These are not fossils of individual creatures, but rather the fossilized remains of entire microbial communities. Billions of cyanobacteria, some of the first life forms to harness the power of photosynthesis, would form sticky mats that trapped sediment in shallow water. Over time, layer upon layer built up, creating distinctive dome-shaped, columnar, or conical structures in the rock. To see a stromatolite fossil in the Canadian Shield is to look directly at the work of trillions of organisms that lived over 2 billion years ago, organisms that were quietly, patiently transforming our entire planet. Their widespread presence here is a direct testament to the shallow, sunlit seas that once covered this land. Alongside the stromatolites, in slightly younger Paleozoic rocks, you find the remains of more complex life like trilobites. These hardy, armored arthropods were the great success story of the early oceans, and finding their fossilized shells in the Shield's limestone is a clear sign that these primordial seas were thriving, dynamic ecosystems long before life ever dared to step onto land. The significance of these ancient Canadian shorelines cannot be overstated. they provide a unique and priceless window into the most pivotal moments in Earth's history. The stromatolites, for instance, are not just pretty rocks, they are the engineers of our modern atmosphere. Those ancient cyanobacteria were the first organisms to develop oxygenic photosynthesis. As they flourished in these shallow seas, they began to pump vast quantities of oxygen, a waste product to them but a miracle for future life, into the water and eventually the atmosphere. This great oxidation event, largely recorded in rocks like those of the Canadian Shield, was the single most important environmental change in our planet's history. It poisoned the atmosphere for many ancient anaerobic life forms but made it breathable for the eventual evolution of complex animals, including ourselves. Therefore, the rocks of the Shield don't just tell us where the ocean was, they tell us how life itself learned to manipulate the entire chemistry of the planet. Furthermore, the chemical composition of these ancient marine sedimentary rocks acts as a time capsule. By analyzing the isotopes of elements like carbon, sulfur, and iron within them, geochemists can reconstruct the temperature, acidity, and chemical makeup of the ancient oceans and atmosphere with astonishing precision. This allows us to track the evolution of our planet from a hostile, alien world with a methane-rich atmosphere to the oxygen-rich, temperate world we know today. Every layer of limestone, every fossilized stromatolite reef, is a data point in the grand story of how a barren rock transformed itself into a living world. The Canadian Shield, therefore, is far more than just a geological formation. It is the closest thing we have to a planetary archive, a place where the deepest past is not hidden, but exposed for all to see, telling the epic story of how life and geology became forever intertwined. Leaving behind the ancient, mineral-rich heart of the Canadian Shield, we now travel to a coastal desert that feels like a different planet altogether, the Namib. Stretching along the southwestern coast of Africa, this is a land of extremes, a place where towering, ochre-colored sand dunes, some of the highest in the world, march right up to the icy, fog-laden waters of the Atlantic Ocean. It is often called the oldest desert on Earth, a hyper-arid landscape where some areas may not have seen meaningful rainfall for over 50 million years. The very name Namib means vast place in the local Nama language, and it is a vastness defined by emptiness, heat, and silence. It is the last place you would expect to find a bustling penguin colony or the skeleton of a great whale. And that is precisely what makes the discoveries here so profoundly disorienting. For deep within this sea of sand, the Namib Desert holds the ghost of a cooler, wetter, and utterly different world, a time when the ocean did not stop at the shore but claimed this land as its own. The evidence for this lost coastline is not buried deep underground. It is often lying exposed on the surface, waiting to be uncovered by the same winds that sculpt the dunes. The most dramatic clues are the fossils. Imagine the surreal experience of a geologist or a curious traveler walking across the barren, gravel plains of the Namib interior, only to stumble upon the massive, bleached vertebrae and skull of a whale, resting on the sand as if it had been dropped from the sky. These are not the remains of lost modern whaling ships. They are the fossilized bones of species that lived millions of years ago, when the waters of the Atlantic Ocean extended dozens of miles further east, submerging what is now a stark desert under a cool, productive sea. Even more astonishing than the whales are the remnants of penguin colonies. Today, the only African penguins are found on rocky islands off the coast. But fossil evidence reveals that these birds once nested much further inland, on rocky outcrops and islands that are now high and dry, surrounded by nothing but sand and stone. Their presence indicates not just a higher sea level, but a significantly different climate, one cool, and moist enough to support the rich marine food webs that these birds depend on. But the story isn't only told in bones. The very shape of the land itself bears the unmistakable signature of the ocean's former reach. In several places along the edge of the desert, you can find clearly defined marine terraces, flat, bench-like features carved into the rocky slopes by the relentless pounding of waves. These are not active coastlines, they are fossil coastlines, raised up and left stranded as the sea retreated. They form distinct horizontal lines on the landscape, like bathtub rings from a vanished ocean, each one marking a specific moment in time when the sea level was stable enough for waves to carve a lasting mark before changing once more. The existence of these features tells a complex story of interplay between two powerful forces: the rising and falling of the global sea and the rising and falling of the land itself. As global sea levels fluctuated due to the growth and melting of polar ice caps, the ocean advanced and retreated across the continental shelf. At the same time, tectonic forces were slowly uplifting the entire coastal margin of southwestern Africa, a process that continues to this day. This uplift effectively raised the old seafloors and wave-cut platforms, preserving them high above the modern waterline and protecting them from being erased by the current waves. For scientists, the Namib is not just a graveyard of ancient sea life. It is a living laboratory for understanding the profound connections between ocean currents, climate, and life itself. The cold Bengla Current that flows northward along this coast is one of the most productive ocean systems on the planet, its nutrient-rich waters supporting enormous populations of fish, seabirds, and marine mammals. By studying the fossils and sediments from the Namib's inland shores, researchers can piece together how the strength and temperature of this current have changed over millions of years. They can see periods when the current was even stronger and colder, driving richer ecosystems further inland, and other periods when it may have weakened, contributing to the aridification of the coast. This history is crucial because it provides a deep time context for the changes we are observing in ocean currents today, helping to predict how they might behave in a warming world. The ultimate lesson of the Namib's hidden shore is one of incredible resilience and adaptation. The ocean retreated, the climate warmed and dried, and the sea became a desert. Yet, life found a way to persist in this new, harsh reality. Many of the creatures that call the Namib home today are marvels of evolution, uniquely adapted to harvest moisture from the thick ocean fogs that roll inland each day. The iconic Welwitschia plant, a living fossil that can survive for over 1,000 years, spreads its long, leathery leaves across the gravel to condense this precious fog into water. Darkling beetles perform a delicate dance, tilting their bodies into the foggy wind to collect droplets on their backs, which then trickle down into their mouths. This entire bizarre ecosystem is in a way a legacy of that lost ocean. The fog that sustains it is a direct product of the cold Bengla Current meeting the hot desert air. Therefore, the Namib Desert stands as a powerful, poetic symbol of transformation. It showcases not just the destructive power of geological and climatic change, but also the creative power of life to adapt, to find a new foothold, and to thrive in the stunning contrast between a watery past and a desiccated present. Our final stop on this global tour of vanished oceans takes us into the heart of the Middle East, to a land of stark and dramatic contrasts, the Iranian Plateau. Enclosed by the rugged, snow-capped peaks of the Zagros and Alborz mountain ranges, this high, flat expanse is a world of searing deserts, salt pans, and seemingly endless sun-baked plains. It feels like the very definition of a continental interior, a place as far from the ocean as one can possibly imagine. And yet, this austere and imposing landscape holds within its rocks one of the most telling secrets of all. It was once the bottom of a warm, shallow sea, a marine crossroads that would ultimately shape the destiny of nations. The evidence for this incredible transformation is found in some of the plateau's most inhospitable places. Take the Lut Desert, a vast hyper-arid basin often called the hottest place on Earth, where ground temperatures can soar to levels that literally bake the soil. It is a place of terrifying emptiness, dominated by giant wind-sculpted sand formations called yardangs and immense fields of sun-cracked clay. Yet, if you know where to look amidst this Martian landscape, you will find the undeniable proof of a watery past. Geologists exploring the Lut have discovered layers of sedimentary rock that are completely out of place for a desert. There are fine-grained limestones and chalky marls, the kind of rock that forms only in calm, deep marine environments. Even more definitive are the fossils. Embedded within these rocks are the ancient remains of oysters, sea urchins, and the tiny, intricate skeletons of ammonites and other cephalopods. Finding the delicate, spiral-shaped shell of an ammonite in the heart of the world's hottest desert is a geological paradox of the highest order, a silent scream from a time when this entire region lay submerged beneath a clear, sun-drenched sea. This was not a fleeting event. For much of the Mesozoic era, the age of dinosaurs, the central Iranian plateau was covered by a vast epicontinental sea. These were not the deep, open oceans we think of today, but rather shallow, warm bodies of water that sprawled across the interiors of continents during periods of exceptionally high global sea levels. The region was part of a larger seaway system connected to the ancient Tethys Ocean, a tropical marine highway that separated the supercontinents of Laurasia and Gondwana. This sea was a thriving world, its waters teeming with life, its calm seafloor steadily accumulating the layers of sediment and organic material that would one day become the bedrock of modern Iran. The eventual retreat of these waters was driven by the same colossal tectonic forces that built the surrounding mountains. The slow-motion collision of the Arabian Plate with the Eurasian Plate acted like a gigantic vise, squeezing the land and pushing it upward, draining the sea and exposing the former seabed to the relentless sun and wind, beginning its long transformation into the desert we see today. But the legacy of this vanished sea extends far beyond fascinating fossils and academic curiosity. It is fundamentally written into the modern geopolitical and economic landscape of the entire Middle East. Those same marine sediments that entomb the ancient sea life are the source of the region's immense wealth. The warm, shallow Mesozoic Sea was an incredibly productive biological factory. Countless trillions of microscopic plankton, algae, and other marine organisms thrived in its sunlit waters. When they died, their remains settled into the oxygen-poor mud on the seafloor. Over millions of years, this thick layer of organic sludge was buried under more and more sediment. The immense heat and pressure from this deep burial slowly cooked this organic matter, transforming it through a complex chemical process into the hydrocarbons we know as oil and natural gas. The porous limestone rocks of the former seafloor became the reservoir, trapping these valuable resources in place. Therefore, the very same environment that left behind fossilized seashells in the Lut Desert also provided the fundamental ingredients for the petroleum that has fueled the global economy for over a century. The story of Iran's oil is at its core the story of its ancient oceans. This deep geological history has also played a profound role in human settlement and culture for thousands of years. The same tectonic forces that raised the plateau and drained the sea also created the basins that now hold vital salt lakes and seasonal rivers. The mineral-rich soils derived from those ancient marine sediments, though often arid, can be incredibly fertile when irrigated, supporting agriculture in oasis towns that have existed since the dawn of civilization. Furthermore, the salt deposits left behind by the evaporation of these ancient seas have been mined and traded for millennia. The human history of the Iranian plateau, the rise and fall of empires, the paths of trade routes like the Silk Road, the locations of its great cities, is inextricably linked to the resources and the topography shaped by these long-vanished waters. The ghost of the Tethys Ocean continues to whisper, not just in the rocks, but in the very patterns of human life and conflict that have unfolded upon them, proving once again that the past is never truly past, but merely buried, waiting to be read by those who understand its language. From the sun-scorched sands of the Sahara to the frozen peaks of the Himalayas, the story these 21 ancient shorelines tell is one of almost unimaginable change, a narrative written not in ink, but in stone, sediment, and fossil. They are the ultimate reminder that the ground beneath our feet is not a permanent stage, but a dynamic, ever-changing page in an epic that has been unfolding for billions of years. These hidden boundaries, concealed thousands of miles from any modern coast, force us to recalibrate our entire sense of time and place. They reveal a planet in a state of perpetual flux, sculpted by the slow, monumental forces of tectonic collisions and the rhythmic pulsing of global climate cycles that raise and lower sea levels like a breath. This isn't just ancient history. It's a deep time lesson in both fragility and resilience. The same processes that drowned entire continents under shallow seas and then raised their seafloors into the world's highest mountains are the very same forces that continue to shape our world today, often in ways too gradual for us to perceive within our fleeting lifetimes. Understanding these lost coasts does more than satisfy our curiosity about the past. It provides us with a crucial framework for navigating the future. By studying how ecosystems collapsed and reformed, how climates shifted, and how shorelines retreated and advanced in response to natural cycles, we gain invaluable insights into the potential impacts of our current period of rapid environmental change. These geological ghosts offer a humbling perspective, reminding us that the environments we depend on are not guaranteed, but are instead the temporary result of a delicate and powerful planetary balance. I hope this journey has inspired you to look at the world with fresh eyes, to see a desert and imagine an ocean, to gaze upon a mountain and picture a seabed. Every landscape holds a secret history waiting to be deciphered. Now I'd love to hear from you. Which of these vanished shores captured your imagination the most? Was it the whale bones in the Australian outback, the ancient reefs of Siberia, or the human story of Doggerland? Share your thoughts in the comments below and tell me what other historical or scientific mysteries you'd like us to explore together next. If you enjoyed this dive into the deep past, make sure to subscribe and hit the notification bell so you don't miss our next adventure. Thank you for watching, and never stop exploring the incredible story of our planet.